Lewis structures. So Lewis bonding theory, we were drawing Lewis structures previously, and we're going to expand upon that a little bit and formalize the rules that we're going to be using for drawing these Lewis structures. And in doing so, there's going to be a couple things that are going to happen. One is that we are going to be breaking the octet rule. So what we said previously is that generally 8 electrons in the outer shell tends to be stable, and that is still true, but there are plenty of exceptions where there are a different number other than 8, and the stability of the atom is still there. One is that you already know is helium, because helium, we've drawn the Lewis dot diagram many times before, and it has only 2 electrons around it, and yet it is incredibly stable. So we've already done breaking of the octet rule. We just want to see some more examples of where it happens to be. And when we follow the systematic naming approach to drawing Lewis structures, we're going to be breaking that octet rule some more. Another thing that we're going to see is the sharing or transference of a double bond. So when you have a substance, a molecule that has a double bond, it may resonate or move from one location to the other. So that can happen with these Lewis structures as well. And we're going to talk about a coordinate bond as well. And that is where a coordinate covalent bond is where both of the electrons that form the bond, normally a bonded pair comes from one atom provides one electron, another atom provides the other electron, and they share, and that's where you get the bond from. But with a coordinate covalent bond, let's say we had, I don't know, a nitrogen or something like that, and draw a Lewis structure for nitrogen. It's got 5 electrons around it, so we can form a bond there, a bond here, and a bond there with, let's say, a hydrogen on each end. What a coordinate covalent bond is when, let's say, a hydrogen that didn't have any electrons at all, so a hydrogen ion showed up. You would think, well, if it doesn't have any electrons, there's no way it's going to be able to form a bond, because a bond is a shared pair of electrons. And if it doesn't have any electrons, how is it going to share any? But if there is a lone pair, that pair itself, even though they both came from the nitrogen, it could form the bond to that hydrogen. So that's what a coordinate covalent bond is. So we're going to go through very systematically the rules for drawing Lewis structures, and we're going to use a bicarbonate ion as our example. So very similar to how you probably started out drawing Lewis structures, we're going to try to put the symbols symmetrically around the central atom. And generally speaking, the central atom tends to be the least electronegative. But if you know how many bonds you're going to be making, roughly, we know hydrogen likes to form 1 bond, carbon likes to form 4, oxygen likes to form 2. So the one that forms the most bond, that's the one we want to be putting in the middle. So we probably want to put our carbon in the middle, and then our 3 oxygens are on the outside. And I'm going to put hydrogen over here for now. While you're doing these, you may make a mistake and you have to go back and rearrange them, because how you arrange them is a little bit awkward and they don't quite bond nicely that way. So sometimes you just have to start over again. All right, the second step is to add up all of the valence electrons for each of the atoms, and then you're going to add in the values for the charges. So if you're dealing with an ion and it has a negative charge, that means it has extra electrons. If you're dealing with an ion with a positive charge, that means it's missing some electrons. So we're going to total up all the valence electrons of the atoms, and then we will decide whether we have to add or subtract any based on the charge. And this is our bicarbonate. So it does have a charge to it. So let's look at this. So hydrogen normally has 1 valence electron. Oxygen normally has 6 valence electrons. There are 3 of those oxygens, so I'm going to add 6 3 times, because each one of them is going to contribute valence electrons to this particular structure. The carbon has 4 valence electrons. So 6 and 6 and 6, we have 18, 19, 20, 21, 22, 23. However, we have a negative charge here, so we've got 1 extra electron. So we're going to have 20, let's add that plus the 1, because it's a negative ion, that means it has 1 extra electron. So I'm going to add 1 more to our total here, and we've got our 24 valence electrons that are going to be placed there. And look at that, did the math right. So what we're going to have to do is use that number of valence electrons, and they're going to have to show up in our diagram. So what we'll do is, since this is a structure, it's being held together, so we're going to start using up, so we've got 24 electrons, we're going to start using them up to build bonds. And remember, every bond is a shared pair of electrons. So we're going to take the 24 electrons, use some of them to form bonds between the atoms. So if we put a bond between the carbon and the oxygen, that's going to hold the oxygen and the carbon together, but that bond's going to take up 2 of the electrons. We're going to put another bond between the other carbon and the oxygen, put one here. That would hold all of the oxygens onto the carbon, and I'm going to bond the hydrogen onto that oxygen. That's going to take up 2, 4, 6, 8 bonds out of the total. So what we had before was 24. We are now down to 16 electrons left. We're going to use the remaining electrons to give the surrounding atoms an octet. So let's put our bonds back in. So that's using up 8 of those electrons. And then we're going to use the remaining electrons to give the surrounding atoms an octet, or basically a full stable valence shell. The hydrogen currently has 2 electrons around it right now. There's 2 in that bond there. And yes, it's sharing them with oxygen, but it still counts as being around the hydrogen. So hydrogen stable with 2 electrons around it. And this oxygen here has 2 electrons on one side and 2 electrons on the other side. So it has 4 electrons. So we're going to need to add in 2, 4 more electrons. Now that oxygen has 8 electrons around it. This oxygen here only has 2 electrons in the bond, so I'm going to have to add 2, 4, 6 electrons around it. And the same with this one. It already has 2 being shared in that bond, so I have to add 2, 4, 6 electrons around it. Let's just make sure I haven't gone past my total. So I used 6 and 6 is 12, 13, 14, 15, 16. So now I'm actually out of electrons. I've placed all of the electrons I have to work with. Then what we're going to do, if we have, let's see if we can do this a little bit faster. Bond, 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 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's our electrons placed. If the central atom doesn't have an octet, so right now it's got 2, 4, 6 around it, doesn't have an octet, I can't just give it 2 more electrons because I don't have any. I've used them all up. So what we're going to do is we're going to take a pair from an outer atom, and we're going to use it to make a double bond. So what I can do is I can take these 2 electrons there, instead of using them as a lone pair on the oxygen, I can put them here as a double bond between the carbon and the oxygen. I haven't taken any away from the oxygen. It still has 8 around it, but now they're being shared, or at least 2 pairs of them are being shared with this carbon as well. So that would give everyone in this structure a full valence shell, and we have a double bond between the carbon and the oxygen. And if you think, okay, well why would I take those 2? Maybe instead of taking those 2, I would take these 2, and that's fine too. It's really, it would look the same thing. We could take those 2 and use them to make a double bond between this oxygen and this carbon, same carbon. That would work too. So either place the double bond could exist. And if there's no difference between the 2 places where the double bond can exist, it could exist in either one of those 2 places. And so we could actually draw a separate option with it existing in the top bond here or existing with this oxygen here. I wouldn't take it from the oxygen that's attached to the hydrogen, because then what I'm going to end up doing is I'm going to form 3 bonds with that oxygen, and we don't normally see oxygen forming 3 bonds. We'll get to more details about that when we talk about bonding itself and what type of bonds are going to be allowed. Last, Let's go through the whole setup again, and we'll see that when we have a ion, we put it in square brackets, and then we put the charge outside of those brackets. If it doesn't have a charge, it's not an ion. If it is an ion, it has to have a charge. So remember, we started with 24 electrons. We used 2, 4, 6, 8 to form bonds. Then we started doing lone pairs, 2, 4, so that oxygen has 8 around it. 2, 4, 6, 8 in the bond there for that oxygen. This one already has 2, 4, 6, 8 around it. So everyone here has a stable valence shell. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've placed all of our electrons. That's how our bonding is going to be. But carbon isn't stable. It only has 6 electrons around it. So we're going to take one of the lone pairs from the atom beside it, and we're going to use that to form a double bond. We haven't added or lost any electrons. We're just moving them from a double lone pair into a double bond. And whether you did it on that oxygen or on this oxygen, it doesn't matter. You could form that double bond in either place, and that's what resonance is. When it can exist in either place equally, it essentially resonates between the two places. It'll be in one place or the other. It'll resonate between the two. So when we follow these rules, we're going to end up breaking the octet rule in a couple of cases, and you're going to see certain ones it happens quite often. So we'll see that in period 2, some of these elements are going to be fine with fewer than 8 electrons, which is okay. We've seen that before. For example, lithium, when it forms an ion, we know it loses an electron. So let's draw the Bohr Rutherford for it for a second. We have 2 electrons in the inner shell, and we have a 3rd electron in the outer shell. But when it forms an ion of lithium plus, we are down to 2 electrons in the outer shell. And a lithium ion is stable. That's why it forms an ion. So it is happy with fewer than 8 electrons. So we're just going to see some more instances of that octet rule being broken. Boron's going to be doing it as well, and beryllium can do it. So if you follow the rules for the Lewis structure, when you draw something with boron, you'll see boron ends up having fewer than 8 electrons. Same thing with beryllium. And in period 3, and remember energy level 3 is where the d orbitals start, there are certain cases where when you follow the rules to draw a Lewis structure, you're going to see elements with more than 8 electrons. So if you were to draw a Lewis structure for phosphorus pentachloride, we're going to end up with more than 8 electrons on the phosphorus just by following those rules. As we mentioned earlier, resonance structures is where the double bonds could be in one place or the other, and there's no reason to prefer one over the other. And so they're actually able to exist in either one of those places, or they're able to resonate between those two places. So here's an example of that. So this is a nitrate ion, and the double bond, if you go to draw the Lewis structure, you could take a lone pair from the top oxygen to make your double bond, or you could take it from the oxygen on the left or the oxygen on the right. So these 3 structures here are all equally as valid, and the double bond could exist in any one of those spots. So essentially it resonates between the 3 spots. All right, let's try this sulfur trioxide molecule. So going through the rules, we're going to start with sulfur in the middle, and then we've got 3 oxygens around the outside. And then we need to count the valence electrons for them. So both sulfur and oxygen are in the same column. They both have 6 valence electrons. So we have 6 and 6 and 6 and 6. And so we are looking at 24 electrons that need to be drawn into our diagram here. So we'll start by forming the bonds. We can use 2 of them to connect sulfur to that oxygen, 2 to that oxygen, and 2 to that oxygen. So that's going to take up 2, 4, 6 out of our 24. So we are now down to 18 electrons. Then we start forming full stable octets with the outer. So let's start with this oxygen. 2, 4, 6. Now it's full and stable. 2, 4, 6. It's got 8 around it. It's stable. 2, 4, 6. That oxygen now has 8 around it there, and I've used 3 groups of 6, so I have used up all of my electrons now. However, the sulfur only has 6 electrons around it. It doesn't have a full outer shell. It's only sharing 6. So what I'm going to do is I'm going to take 2 of these lone pair electrons, and I'm going to instead form a double bond with them to the sulfur. Now, whether I did it there, or let's put these electrons back there, I could use the valence electrons from this oxygen on the top right there. That would be fine too. So since it could exist in any one of these 3 locations as a double bond, not all of them at the same time, one or the other, that's called resonance. It can resonate between the 3 different locations. And there is our stable Lewis structure. And realize oxygen is only forming 1 bond here, which you may be a little bit uncomfortable about, but it does have 8 around it, so we are following all the rules for the Lewis structure. Now, when we look at something like that, we may say, okay, well, that doesn't seem quite right. And so often there can be various Lewis structures that you can draw for the same molecule. And we want to have different ways of evaluating which is the best Lewis structure. Because following the rules, you could end up with one or another, and you have to have a way of differentiating which one's better. One of the ways to do that is called formal charges. And essentially what this looks at is to say, okay, well, how many electrons does the atom normally have around it, and how many does it have it around it in your Lewis structure? And if that number is close, that's a good thing. It's going to be more stable. If it is high, it's going to be less stable. So if you have a hydrogen in your Lewis structure, and you know that hydrogen normally has 1 electron around it based on the shell that it's in, it normally forms 2 in a bond. If you have a structure that has like 8 bonds around hydrogen, that's not going to be very stable. So the one with the smallest formal charges, and this is a system for checking for stability essentially, is going to be a more correct structure, even though it may break the octet rule. So how we do this is that we look at each atom in the structure, and we assign each atom in the structure a formal charge based on how many electrons it has compared to how many it normally has. And here's the calculation for what we mean by that. So we're going to find the formal charge, and it's going to be based on the group number, which is essentially the valence number of electrons. We're going to take that and we're going to minus the non-bonding electrons around the atom, so the lone pairs, and we're going to subtract half the number that are in the bonds. So each bond has 2 electrons in it, so for every bond we subtract 1 electron. The more atoms that we get with a formal charge that is closest to 0. So essentially we want low formal charges. If your structure has low formal charges, it's a better structure. So for NO2, if we try drawing a Lewis structure for NO2, we could end up with, say, these 3 different structures here. We're using the same number of electrons in each one, so all of them could have been drawn using the rules from our our Lewis structure drawings. So what we could do then is we can say, okay, well, which one's better? And we'll do that by calculating the formal charges. So let's use that calculation again. Let's look at oxygen. Every atom in this structure here, both of the oxygens and the nitrogen, we want to calculate its formal charge and figure out what it would be. So remember, the calculation for it is the valence number that it is. So oxygen has, let's just do the calculation for this one. Oxygen has 6 valence electrons, and we're going to subtract from it the number of lone electrons. And this one, the way it's drawn here, has 6, so 6 minus 6. And we're going to minus half the number that are in the bond. So this bond here has 2, So we're going to minus half of 2, which is 1. So that particular oxygen ends up with a formal charge of -1. So let's just write that up at the top here. This guy has a formal charge of -1. Now let's do the nitrogen. So I'll do that in different colors so we can see. So let me just circle these because it's sort of a quick way of getting the formal charges. So nitrogen normally having 5 valence electrons. In this particular way that we have drawn it, it has 1 unbonded electron, and it has 3 bonds around it. Each bond has 2 electrons. So we take that 6 electrons in the bonds, we take it by half. So we're going to minus 3 electrons from that. So the formal charge on that nitrogen is going to be a +1. Let's just write that above it. +1. And let's do the formal charge on this last oxygen. Again, it has a valence of 6 electrons normally. So we're going to subtract from it the number of lone electrons. So we've got 2 lone pairs, so that is 4 electrons. And then we're going to subtract from it the number of electrons that are in bonds divided by 2. There's 2 bonds, that's 4 electrons each, so we're going to subtract 2 from that, and that's going to equal 0. So for this Lewis structure right here, it has the formal charges of -1, +1, and 0. So they're not terrible, but the more that are closer to 0, the better. And you can sort of start to see how you can get a little bit faster at calculating formal charges. I'm drawing a circle around it and that cuts the bond in half, and that makes sure that I count half of the number of the electrons in that bond. So essentially then all I have to do is say, okay, well that's oxygen, so it's 6 minus 1, 2, 3, 4, 5, 6, 7 in this case. So that equals -1. So there's a -1 formal charge. Let's do the nitrogen. So nitrogen normally has 5 as its valence, and I've got the 2 as lone electrons, unbonded electrons, and I've got 3 as the ones that 3 bonds. So half of that number of electrons in the bonds is 3. So I have, let's write that out once more, 5, and I'm going to subtract the 2 unbonded electrons and the 3 electrons from the bonds, and I end up with a 0. So nitrogen has a formal charge of 0 in that one. And in this one, and you'll start to see, okay, I've circled the electrons essentially that I have to subtract from the valence. So I've got 6, and I've circled in there 1, 2, 3, 4, 5. So that is going to be +1. So this one here has formal charges of -1, 0, and +1. So it's no better than the first option. Let's try the third option. So same way, we followed rules to draw it, and we could have ended up with this structure. This oxygen here has a formal charge of, this nitrogen here has a formal charge of, and this oxygen here has a formal charge of. So of the 3 structures, this one at the end here has 3 zeros as its formal charges, so it has more formal charges closer to 0. So that is the best structure. The other ones are still done following the Lewis rules, but it's not as stable as this one at the end here.